Chapter 5. In the chapter all about electromagnetism, let us see how interaction between electric current and magnetic field takes place. Students, place a white paper on a drawing board and place a bar magnet in the middle of the paper. Sprinkle some iron filings on it. Tap the board gently. What do you observe? You must have seen a transformer on a road, electric doorbell or ding-dong, speaker, electric water pump, generator, radio, television antenna. Have you ever thought about the working? The answer is electromagnetism. Look at the picture. Sharp and heavy iron scrap material is attached to a big disc. The disc is a magnet and all scrap is attracted to it. This process is used in loading and transporting scrap and loose iron material in a steel mill. It is not feasible to create a permanent magnet of such a big size and store such a big magnet. Therefore, magnetism is induced in the disc with the help of electricity. Such a magnet is called electromagnet. Let us perform this activity. Take a drawing board and fix a white sheet of paper on it. Place a bar magnet at the center and draw its outline with the help of a pencil. Place the magnetic needle close to any pole. Wait till the needle comes to rest. Draw the dots with pencil as shown. Go on marking till the needle comes to the other end or pole. Draw a smooth curve using dots. Repeat the process to plot other smooth curves as shown. Let us see what is meant by magnetic lines of force. The path along which the unit north pole moves in the magnetic field is called magnetic lines of force or magnetic field lines. Properties of magnetic lines of force. 1. Magnetic lines of force are closed continuous curves. They start from north pole and ends on south pole. 2. The tangent at any point on the magnetic lines of force gives the direction of the magnetic field at that point. 3. No two magnetic lines of force can intersect each other. 4. Magnetic lines of force are crowded where the magnetic field is strong and far from each other where the field is weak. Let us try out this activity. Make the circuit by connecting the two terminals of the electric cell to the key as shown. Place the compass needle close to it. Note the direction in which compass needle is pointing. While watching the compass needle carefully, close the key for few seconds. Release the key and watch again. Repeat the steps again by changing its polarity. In the above activity, it is observed that the needle gets deflected when we press the key. If the polarity is reversed, the needle gets deflected in the opposite direction. Thus, if a current is passed through a wire, electric field is produced near it. This was discovered by the scientist Ørsted. He showed that electricity and magnetism were related phenomenon. Danish physics professor Hans Christian Ørsted was doing experiments with some electrical equipment. He saw that when he passed strong electric current through a wire, a nearby compass needle got deflected. Ørsted realized that the electric current was producing magnetism. A compass needle is a small bar magnet. The ends of the compass needle point approximately towards north and south directions. The end which points towards north is called as North Pole or North-seeking pole. The end which points south is called as South Pole or South-seeking pole. Like magnetic poles repel each other and unlike poles attract each other. Let us do this activity. Take a battery of 12 volt, a variable resistance or rheostat, an ammeter of 0 to 5 amperes, a plug key, needle and a long straight thick copper wire. Take a rectangular cardboard, pass this wire through the center. Take care that the cardboard is fixed and does not slide up or down. Make the arrangement as shown. Sprinkle iron filings uniformly on the cardboard. Close the key and tap the cardboard gently. Observe the pattern of iron filings. What will happen if the current is increased? More magnetic lines are produced. Also observe the needle if it is moved away from the wire. The number of magnetic lines decreases. Let us see about magnetic field due to current carrying conductor. In the above activity, if we increase the current through the wire, the needle will deflect more, and if we move the compass away from the wire, the deflection in the needle will start decreasing. Thus, 1. Magnitude of the field produced at a given point is directly proportional to the magnitude of the current passing in the wire. 2. Magnetic field produced by a given current in the wire decreases as the distance from the wire increases. Right hand thumb rule. Imagine you are holding a current-carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then the curled fingers around the conductor will give the direction of the magnetic field as shown. This is known as the right hand thumb rule. Let us do this activity. Take a rectangular cardboard with 2 holes. Take a coil of large number of turns. Insert the coil through the holes such that the turns are normal to the plane of the cardboard. Connect the 2 ends of the coil in series with a battery, a key and rheostat as shown. Sprinkle iron filings uniformly on the cardboard. Plug the key, tap the cardboard gently. Observe. As the key is plugged, the iron filings form the concentric circles around the poles of the coil. Let us move to the next topic, magnetic field due to a current through a circular loop. It is seen that at every point of the loop, the lines are in the form of concentric circles. But these circles would become large as we move away from the wire. At the center of the loop, the areas of these circles would appear as straight lines. The magnetic field produced by a current-carrying wire at a given point depends directly on the current passing through it. Thus, if a coil has n turns, the field produced is n times larger than that produced by a single turn. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Activity. Wind the insulated wire tightly around the nail in the form of coil. Connect the free ends of the wire to 2 terminals of the cell for few seconds. Bring small iron pins near the tip of the nail and observe. Disconnect the wire ends and observe. Even after disconnecting the wire ends, pins get attracted towards the tip of the nail. Repeat the above steps again. What do you conclude? We can see that the nail is acting as a magnet here which attracts the iron objects towards it. Magnetic field due to current in a solenoid. A coil of many turns of insulated copper wire wrapped in the shape of a cylinder is called a solenoid. The magnetic field lines in a solenoid through which current is passed are shown here. These lines are similar to that of the lines of a bar magnet. One end of the coil acts as south pole and the other end as north pole. Thus, solenoid has all the properties of the field produced by a bar magnet. With the help of a solenoid, we can magnetize a piece of rod of a given material. If the rod is hard steel and if the magnetic field is strong enough, a permanent magnet can be produced. Permanent magnets are usually made of carbon steel, chromium steel, cobalt and tungsten steel, and some alloys. Two such alloys which are used in industry are Niperimag and Alnico. Niperimag is an alloy of iron, nickel, aluminium and titanium. Alnico is aluminium, nickel, cobalt alloy of iron. Permanent magnet of such alloys are used in microphones, loudspeakers, electric clocks and many other devices like ammeters, voltmeters and speedometers, etc. Activity: take a small aluminium rod AB. Suspend it horizontally by means of two connecting wires from a stand. Now place a strong horseshoe magnet in such a way that the rod is between the two poles with the field directed upwards. If a current is now passed through the rod from B to A, you will observe that the rod gets displaced. This displacement is caused by the force acting on the current-carrying rod. The magnet exerts a force on the rod directed towards the right, with the result that the rod will get deflected to the right. On reversing the current or interchanging the poles of the magnet, the direction of the rod will reverse. This indicates that there is a relationship among the direction of the current, the field, and the motion of the conductor. Force on a current-carrying conductor in a magnetic field. Electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André-Marie Ampère, 1775 to 1836, suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. In the above activity, it is seen that the rod is displaced, which suggests that force is exerted on the current-carrying aluminium rod when placed in the magnetic field. The direction of force depends on the direction of the current and the direction of magnetic field. The displacement of the rod is maximum when the direction of the current is at right angles to the direction of magnetic field. Let us learn Fleming's left-hand rule. Stretch the forefinger, the central finger, and the thumb of your left hand mutually perpendicular to each other. If the forefinger shows the direction of the field and the central finger shows the direction of the current, then the thumb will point towards the direction of the motion of the conductor. Current is a flow of charge. This means that moving charges in a magnetic field would experience a force. This property is used to accelerate charged particles to very high energies. These high energies of the particles are used to study structure of the matter. Let us look at the use of magnetism in medical sciences. Electric current produces magnetic field even if the current is very weak. Ion current, which is very weak and which travels across the nerve cells in our body, produces magnetic fields. If we touch something, our nerves carry an electrical impulse to the muscles we need to use. This produces weak magnetic field. Heart and brain are the two main organs where significant magnetic fields can be produced. This forms the basis of obtaining images of heart and brain or images of different parts of the body. This is done using a technique called magnetic resonance imaging, MRI. Analysis of these images help doctors for diagnosis of disorders of brain. Let us try out this interesting activity. Take 3 ring-shaped magnets, insulated copper wire of 1.5 meters, battery and paper clips. Cut the wire into 3 pieces, one piece about 1 meter and the other 2 into 0.25 meters each. Take 1 meter piece of wire and wrap this wire around 2 fingers to form a coil. Take loose end of this wire, wrap it once along the diameter of the coil. The 2 arms of the coil should be directly opposite to each other. Bend the paper clip and prepare the holder for the coil. Pile the 3 magnets on the table. Position the coil above the magnet on paper clip holder. Take free ends of the wire and connect them to the battery as shown. Give a gentle spin to the coil and what do you observe? We can see the coil rotating. Let us learn about the electric motor, a device which converts electrical energy into mechanical energy is called an electric motor. Principle: electric motors work on the principle that a current-carrying conductor placed in a magnetic field experiences a force. Construction: armature coil. A large number of turns of insulated copper wire wound on iron core in rectangular shape forms an armature coil ABCD as shown. Strong magnet. The armature coil is placed in between 2 pole pieces, N and S of a strong magnet. This provides a strong magnetic field. Split ring commutator. It consists of 2 halves R1 and R2 of a metallic ring. The ends of the armature coil are connected to these rings. Commutator reverses the direction of current in the armature coil. Brushes. 2 carbon brushes, B1 and B2, are used to press the commutator. Battery. The battery supplies the current to the armature coil. Working of the electric motor. When current is passed through the coil ABCD, arms AB and CD experience force. According to Fleming's left-hand rule, the force experienced by arm AB is in the downward direction and arm CD in the upward direction. Both these forces are equal and opposite. This force rotates the coil in clockwise direction until the coil is vertical. At this position, the contact between commutator and brushes break, so the supply to the coil is cut off. Thus, no force acts on the coil, but the coil does not stop due to inertia. It goes on rotating until the commutator again comes in contact with the brushes B1 and B2. Again, the current starts passing through coil and the arm AB rotates through 90 degrees, 180 degrees, 270 degrees and 360 degrees. Now the force acting on arm AB is downward and CD is upward. Again, this force moves the coil in clockwise direction. Thus, the coil rotates with the help of electrical energy. The coil of DC motor continues to rotate in the same direction. Uses of DC motor. 1. These motors are used in domestic appliances like mixers, blenders, refrigerators and washing machines. 2. These motors are used in electric fans, hair dryers, record players, tape recorders and blowers. 3. These motors are used in electric cars, rolling mills, electric cranes, electric lifts and electric trains. Magnetic levitation trains do not run on rails but float above them. A current passes through the electromagnets in the track and on the train. The magnetism produced lifts the train upwards. Try this out. Take a coil AB having 10 to 15 turns. Connect the two ends of the coil to the galvanometer. Take a strong bar magnet. Move the north pole of the magnet towards the B end of the coil. Observe the deflection in the galvanometer. Note the direction of the deflection, that is, right or left. Now repeat this with the south pole. Again observe the deflection. Note its direction. What will happen if instead of magnet a coil is moved? If both coil and magnet are kept stationary, do you observe any deflection? No, deflection is not observed. Let us perform one more activity. Take two coils of about 50 turns. Insert them over a non-conducting cylindrical roll as shown. Thick paper roll can be used. Connect coil 1 to a battery with a plug key. Connect coil 2 to a galvanometer. Plug the key and observe the deflection in the galvanometer. Unplug the key and again observe the deflection. No deflection can be seen in the galvanometer. Let us study what is meant by electromagnetic induction. When a current carrying conductor is placed in a magnetic field such that the direction of current is perpendicular to the magnetic field, it experiences a force. But if a conductor is moving inside a magnetic field or magnetic field is changing around a fixed conductor, electric current is generated. This was first studied by Michael Faraday. Here, if you had moved south pole of the magnet towards end B of the coil, the deflection would be opposite to the previous case. If both coil and magnet are stationary, there is no deflection in the galvanometer. Thus, the motion of a magnet with respect to the coil, or if coil is moved with respect to the magnet, potential difference is induced, which sets up an induced electric current in the circuit. Here it is seen that if the current in the coil reaches either steady value or zero, the galvanometer connected to coil 2 shows no deflection. Thus, potential difference is induced in the coil 2 whenever the electric current through coil 1 is changing. Coil 1 is called as primary coil and coil 2 is called as secondary coil. As the current in the first coil changes, the magnetic field associated with it also changes. The process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Fleming's right-hand rule. Stretch the thumb, forefinger and middle finger of the right hand so that they are perpendicular to each other as shown. If the forefinger indicates the direction of the magnetic field and the thumb shows the direction of the motion of conductor, the middle finger will show the direction of induced current. The induced current is found to be the maximum when the direction of motion of the coil is at right angles to the magnetic field. A galvanometer is an instrument which is used to detect the presence of current in a circuit. If the current in a circuit is zero, the galvanometer will show zero deflection or no deflection. The deflection is on either side of the zero mark depending on the direction of the current. Michael Faraday in 1821 found that electricity could produce rotary motion. Today's electric motors are based on this. In 1831, he showed that relative movement between a magnet and a coil of wire would induce electricity in the coil, an idea which gave birth to modern generators. Question. Observe the figure. If the current in the coil A is changed, will some current be induced in the coil B? Explain. Yes, after changing the current in the coil A, current will be induced in coil B. If we switch off the current in coil A, the pointer of galvanometer attached to coil B shows a momentary deflection but on the opposite side. This means that on switching off current in coil A, an electric current is induced in coil B, but in a direction opposite to that when the current was switched on. If we keep on switching the current on and off in coil A rapidly, then the galvanometer pointer will keep moving on both the sides of zero mark continuously, showing that a continuous current is induced in coil B. Since the current induced in coil B changes direction continuously, so it is an alternating current. From this, we conclude that whenever the current in coil A is changing, then an electric current is induced in the nearby coil B. Very useful application based on the principle is galvanometer. A galvanometer is an instrument which is used to detect the presence of current in a circuit. If the current in a circuit is zero, the galvanometer will show zero deflection or no deflection. The deflection is on either side of the zero mark depending on the direction of the current. What is meant by direct and alternating current? There are two types of currents. One, direct current, DC, and two, alternating current, AC. Direct current always flows in one direction, and alternating current reverses its direction periodically. Most of the power stations produce alternating current. In India, the frequency of alternating current is 50 Hz. An important advantage of alternating current over direct current is that electric power can be transmitted over long distances without much loss of energy. Let us compare DC and AC now. First, for DC, magnitude and direction both are constant, whereas for AC, magnitude and direction reverses periodically. Second, DC cannot be used for large-scale electricity for household purpose, whereas AC is used for large-scale applications. Third, frequency of DC is always zero, whereas frequency of AC in India is 50 Hz. Let us study about electric generator. An electric device which converts mechanical energy into electric energy is called an electric generator. Principle: electric generator works on the principle of electromagnetic induction. When the coil of electric generator rotates in a magnetic field, the magnetic field induces a current in this coil. This induced current then flows into the circuit connected to the coil. Types of electric generator: AC generator, DC generator. AC generator: a generator which converts mechanical energy into electric energy in the form of alternating current is called AC generator. DC generator: a generator which converts mechanical energy into electrical energy in the form of direct current or DC is called as DC generator. AC generator construction: the main components of AC generator are as shown: armature, strong magnets, slip rings and brushes. Armature, strong magnets and brushes are the same as used for electric motors. Slip rings: the two ends of the armature coil are connected to two brass slip rings R1 and R2. These rings rotate along with the armature coil. Working: when the armature coil ABCD rotates in the magnetic field provided by the strong magnets, it cuts the magnetic lines of forces. Thus, the changing magnetic field produces induced current in the coil. The direction of induced current is determined by the Fleming's right-hand rule. The current flows out through the brush B1 in one direction in the first half of the revolution and through the brush B2 in the next half revolution. In the reverse direction, this process is repeated. Therefore, the induced current produced is of alternating nature. Such a current is called as alternating current. DC generator or dynamo. Construction. The main components of DC generator are 1. Armature coil, 2. Strong magnets, 3. Split rings or commutator, 4. Brushes, 5. Bulb. The components such as armature coil, strong magnet, brushes are the same which are used for AC generators. Split ring or commutator is the same as used in electric motor. 5. Bulb. The output is shown by the glowing bulb connected across the carbon brushes. Working of DC generator. When the coil of DC generator rotates in the magnetic field, potential difference is produced in the coil. This gives rise to the flow of current. This is shown by glowing of the bulb. In DC generator, the flow of current in the circuit is in the same direction as long as the coil rotates in the magnetic field. This is because one brush is always in contact with the arm of the armature moving up, and the other brush is in contact with the arm of the armature moving downward in the magnetic field. Students, try to draw a sketch diagram of electric supply from your electric meter to any room in your house. Let us look at the domestic electric circuit. State Electricity Board provides us with the electric power supply for houses and factories. This is supplied through underground cables or overhead wires on poles. These wires or cables are of three types: phase wire or live wire, neutral wire, and earth wire. These wires coming from power substations are connected to an electric meter installed in a house or a factory. The potential difference between the live wire and neutral wire is between 220 volt to 250 volt. The output power from electric meter is taken to the main switch. A fuse known as main fuse is placed in the path of live or phase wire. The output electric power from the main switch is distributed to the domestic electric circuit. This shows a schematic diagram of one of the common domestic circuits. In each separate circuit, different appliances can be connected across the live and neutral wires. Each appliance has equal potential difference. They are connected parallel to each other. What are the safety measures to be taken in using electricity? Electric fuse. An electric fuse is a safety device used to save the electrical appliances. Wires carrying electricity should not be touched barefooted. If we touch the wire barefoot, a large current may pass through our body, so we may receive severe shock. This shock may sometimes cause death. Therefore, while working with electricity, we must wear gloves made of insulated material and rubber-soled shoes so that current may not flow through our body. The insulation of the wire must be checked periodically. Earthing. Many electrical appliances have a metallic body such as electric heater, toaster, oven, refrigerators, etc. If by chance insulation of the wire melts, the live wire may touch the metallic body of the appliance. If we touch this body with bare hands, we may receive a severe shock. To avoid such accidents, Metal casings of all electrical appliances must be earthed. One end of a copper wire is connected to the metal case of the appliance and the other end is connected to the copper plate which is buried deep inside the earth. This system of connecting the metal casting of an electrical appliance with a copper plate buried deep inside the earth is called as earthing. Electric circuits should be switched off during lighting. This will save the electrical appliances from burning. What is meant by short-circuiting and overloading? Short-circuiting. If a live wire and a neutral wire come in direct contact or touch each other, short-circuiting takes place. During a short circuit, the resistance of the circuit becomes very small and hence huge amount of current flows through it. This produces a large amount of heat and raises the temperature. As a result, the circuit catches fire. Overloading. Overloading means the flow of large amount of current in the circuit beyond the permissible value of current. If many electrical appliances of high power rating such as geyser, heater, motor, oven are switched on simultaneously, overloading occurs. This causes fire. This can be avoided by not connecting many appliances in the circuit. Well, that ends the chapter. Hope it was a joyful learning. You have the options to view a mind map for a quick recap and a question and answer section to study the exercises. Wish you all the best. Bye till we meet again.